Okay, hello, this is Dr. Mohammed, and this is another video under Design of Steel Structures according to AISC. Today we are going to talk about part 5 of beams, and it is going to be the last part. And in today's video, the contents or beam design charts. I'm going to talk about it and elaborate on this topic because it's important how to use the design charts in general, and especially whenever that you are designing and using the wide flange. It is most commonly used shape, and this is commonly used in design offices. And in the same time, I'm going to give or provide a couple of examples. They are going to provide for us how to use these design charts in more details, and we are going to get familiar with using the design charts based on that. Okay, now let's go to the next, the first part, which is the beam design charts, and understand more about it. First of all, we need to know that there are many graphs, charts, and tables are available for practicing engineer. You're going to find this everywhere whenever that you are going to work in a design office or in a firm or a company. And these aids can greatly simplify the design process. But for the sake of efficiency, they are widely used in design offices, but you should approach their use with caution. And this is an important issue here. You need to be careful when you are using these design charts and do not allow basic principles to become obscured. And that's the main point here, that you need always to understand the basic principles behind these charts and the basic equations and formula that are already used or have been implemented in order to make these charts. And always you need to have an intuition and judgment and engineering sense regarding whatever that you are doing. Okay, so these design charts, as we said, it should be approached with a great deal of caution. It is not our purpose to describe in this book all the available design aids in detail. Actually, this is the textbook that I'm following, so we are not going to describe everything in detail regarding the design charts, but some of them worthy of note, particularly curves of moment strength. This is the most commonly used charts versus unbraced length and you're going to find this in part 3 of the manual. Okay, these curves will be described with the reference of figure 525. As you can see here, these figures actually that I'm going to show to you part of it in a minute, you are going to find it something like this in the manual. Okay, and you are going to find that there are vertical axis and horizontal axis. The vertical axis is labeled by two different numbers here. Okay, and the horizontal axis, it is going to be the horizontal or the unbraced length. Let's go back to this simple chart that is representing what we are going to see in these chart, this figure that is representing what we're going to see in the charts. So commonly on the horizontal axis, we are having the unbraced length, LB, and on the vertical axis, we are having the nominal strength, or the nominal flexure strength, of course, it is MN. And you are going to find something like this curve here. And as we have explained before, the horizontal line of this part is representing M plastic. This is the plastic flexural moment that can be developed for compact sections, and we said this is considered to be higher even than yield. And after that, until we reach to a point here which is solid point, take care of this, it is solid, not hollow, because here it is going to be hollow point on the curve. The solid point is making differentiation, or it makes difference or divides the space into part related to the plastic, flexural plastic moment, and here starting the part of lateral torsional buckling, whether it is going to be inelastic or elastic. Okay. Okay, lateral torsional buckling, and here inelastic lateral torsional buckling, as you know, and we have discussed this many times before. So there is a solid line, solid dot here, circle, that is going to be giving us or dividing up the space where that here is plastic part, here it is the start of the lateral torsional buckling part, and this is on the horizontal line is going to be represented by LP. Okay, P stands for plastic. So this is the LP. And after that, we are going to find another hollow circle, as you can see it here. And this hollow circle is represented on the vertical axis with MR, okay, and the horizontal axis, it is represented by LR, okay. So this is MR, which is the proportional limit distinguished between the inelastic part and elastic part of the lateral torsional buckling. So we are going to see this as like hollow circle. It is hollow circle, remember that. But here it is like a solid circle is going to be found here. Okay. So remember, this is the shape of the chart or the curve that you're going to see in the chart. This is an example was given for wide flange 24 by 146 F yield, as we are going to see that these charts are only for wide flange, and you can find it for C and MC, which is the channel and miscellaneous channel curves as well. But we are highly interested in wide flanges, and it is for F yield, as you can see, equal to 50 KSI. And this is for compact. Of course, we are talking about compact because we have the horizontal line here. It is in plastic. Okay. If we are having non-compact, then the horizontal line should not be here, and it's going to be somewhere here, and it represents the flange local buckling. Okay, not the plastic moment or flexural moment of plastic flexure moment of the section. Okay. Okay, so this is only like some hints about what we are going to see on the charts. One very important thing that is related to the charts in general, not this particular chart, is that we are dealing with them under the consideration of CB equal to 1. So this means that we are considering, or the charts are considering CB to be 1. So what if that you are going to have, for example, a case where that CB equal to 1.3? In this case, you need to multiply whatever the moment capacity that you are obtaining from the charts by the real value of CB that you are dealing with in this case. Okay. So, or otherwise, the required strength that you needed, for example, M ultimate that is coming from the load combination from the very first beginning, you can divide it by the value of the real CB that you have, 1.3, and then you can enter the curve using this value to check whether that it is within the capacity or not, as we are going to see in a minute. Okay, these curves will be described with reference, as we have mentioned with this figure, which shows a graph of nominal moment strengths as a function of unbraced length, which is LB, for a particular compact shape. So this is compact shape. Okay, this is compact shape, and the horizontal line, as you can see here, is denoting MP. Such a graph can be constructed for any cross-sectional shape, and effective and specific values of F yield and CB by using the appropriate equations for moment strengths that we have studied in the previous videos. Okay. Okay, now let's go to another point which is important for us to note about the curves. The design charts in the manual comprise a family of graphs similar to the one shown in the figure before, which is this one. We have a family of curves in the manual. Two sets of curves are available, one for wide flange with F yield equal to 50 KSI, and one for C and MC This is C, or channels, and MC, which means that miscellaneous channels, non-standard channels shapes, with F field 36. So we have here two different shapes. Wide flange, remember well, with F field equal to 50 KSI, and we have C or MC, and they are going to be with F field equal to 36 KSI. Okay, so these are two families, two different shapes that we are going to use. Commonly we are going to use the wide flanges, or commonly you are going to find that wide flanges is the most commonly used curves. Okay, even that the channels also you can find it, but anyway, wide flanges are commonly used for us. Each graph gives the flexure strength of a standard hot rolled shape. So we are talking about hot rolled shape. Okay, it's not built up sections. Built up section you need to go and calculate it by your in-house calculation sheets or so. And instead of giving the nominal strength Mn, however, both the allowable moment strength and the design moment strength are given. This is the allowable, which means that ASD, so for ASD Mn over omega, or the safety factor, okay, and this is related to ASD. For LRFD, you're going to find that it provides directly phi b times Mn. Okay, both of them, they are going to be given in the vertical axis. So you're going to find the vertical axis, you're going to find numbers here, and this is under LRFD, for example, and another numbers adjacent to it, and it is based on ASD. This is, as we said, the allowable moment strength or the design moment strength. See? So we're going to find here, this is ASD, this is LRFD, and this is ASD, as you can see here. And you're going to find the numbers are arranged here. And this is the allowable moment strength, okay, or the design strength, whether that you are going to read it based on LRFD or ASD. Remember that we are talking about F field equal to 50 and CB equal to 1. Okay, this is the available moment on the vertical axis. The horizontal axis is going to give us the unbrazed length. Take care of the units being used. Okay, the units that being used here, kip foot. Okay, and here it is in foot as much as I can see. Okay, 4 foot increment. So maybe it's not 1 foot here. It is the increment maybe by 4 foot or 4 feet. I mean, that is 4, 8, 12, and so on. Okay. Okay. So this is how it works here. Two scales are shown on the vertical axis, one for the allowable strength, another one for the design strength. All curves are generated with CB. You can find it easily here. CB equal to 1. For other values of CB, simply multiply the moment from the chart by CB. So whenever that you are going to have available moment, for example, phi b times Mn for LRFD, then multiply it by CB. If CB other than 1, if it's, for example, 1.3 or 1.2 or whatever, then you need to multiply to get the available strength. Okay, however, the strength can never exceed the value presented by the horizontal line at the left side of the graph. This is an important issue. What is the meaning of this? Sometimes when you are going to multiply your value with the CB, sometimes CB is 1.67, for example. And when you are going to multiply, you're going to find, let's see here. Okay, let's assume that you multiplied, you have value of the moment on LRFD and Kip's foot. It is 7, for example, 7,500, something here. And you have 7,500, okay? And you have CB, it is 1.5, for example. This is CB. Then it is going to give you something more than for sure, more than, it is around maybe 1,000. Okay, sorry, yes, 10,000. 10,000, right? 1.5 times 7,000 something, more than, okay? It is larger than. Okay, look here, this curve, this line, it is white flange something here, and whenever that you multiply, you're going to find that your level of strength for this shape, if you are going to use this shape, is going to be here, something that is large enough, more than 10,000, maybe here, okay? This means that you cannot use this shape. The maximum plastic limit for this shape is here, for example, which is maybe 8,000 something, I'm not sure, okay? So whenever that you multiply whatever the required strength by 1.5, okay, which is the CB, the value of the CB, and the value, the total value is going to be higher than the plastic moment. This is MP, plastic moment, horizontal line. I'm talking about the horizontal line. If you are talking about this curve, for example, this means that you need to limit your strength by this value. Okay, you need to limit your strength by this value. This is what I'm going to show this in the example, so do not worry about this. Okay, so but keep it in your mind, the strength can never exceed, take care, we are talking about the strength, can never exceed the value presented by the horizontal line at the left side of the graph. For a compact shape, this represents the strength corresponding to yielding, which reaching the plastic moment. And if the curve is for a non-compact shape, the horizontal line represents the flange local buckling strength. As I said, I'm going to show to you, we have like, this is the curve that we usually have, right? Horizontal line for compact shapes, if we're talking about compact, the horizontal line means that MP, right? Plastic moment. But if we are going to find if this shape is not compact, it is non-compact, then the horizontal line in this case is not going to be MP. It is going to be based on flange local buckling. Because it's non-compact, it cannot reach MP. And also the web is going to be compact, as we know, for hot rolled. So we are always concerned with the flange local buckling. Okay, so it depends whether that our shape is compact or non-compact. Okay, you are not going to find on the charts or in the curves whether that this shape is compact or not. They are not distinguishing, they are not giving any hint about this. You need to know whether that your shape is compact or not from the tables, other tables. And then whenever that you enter the curves and the charts, you need to keep in your mind that this shape is compact, then the maximum horizontal line here is going to be MP, or this shape is non-compact. In this case, we are going to use flange local buckling. Okay? Okay. And I'm going to show this in detail, okay, in the next, in the example. Okay, there is another thing. Whenever that you are entering the graph, you need to know how your curve is going to be sufficient for the required strength and the unbraced length that you are having. So assume that you have a required strength, horizontal dashed line is representing here, and you have unbraced length, which is represented by this vertical dashed line, and this dot is the required cross-section. Whenever you look at this, you need to choose one cross-section or one curve that is satisfying this. Whenever you are looking to this point, you need to look up or to the right. So whenever you go up, the first curve, the first solid curve, take care of the word solid here, solid curve that is going to encounter you, then you can use it because its nominal strength, okay, nominal strength is going to be higher than the required strength that you need. Or if you are searching for the unbrazed length to be higher, then you can go to the right until you find the solid curve, the first solid curve, and this would provide for you available strengths equal to the required strength, but the unbrazed length is going to be higher for this cross section. Okay, this means that you need to look up or right. This is for short what you should do. Look up or right from this point. Okay. Let's read this, and I'm going to give some elaboration about specific points here. Where two such curves are shown, okay, in this charts we have like two curves here. Any point on this graph, such as the intersection here of the two dashed line, represents an available moment strength and unbrazed length. It is available strength and unbrazed length. Okay. If the moment is required moment capacity, if is a required moment capacity, then any curve above the point corresponds to a beam with a larger moment capacity. Okay, so as I said, you're going to go up. And any curve to the right is for a beam with exactly the required moment capacity, although for a larger unbrazed length. This is larger unbrazed length. In a design problem, therefore, if the charts are entered with a given unbrazed length and a required strength, curves above, take care of this, above and to the right, okay, of the point correspond to acceptable beams. Correspond to acceptable beams. So you need to look to the left, to the right and up always. If a dashed portion of a curve is encountered, then a curve for a lighter shape lies above or to the right of the dashed curve. This means that if you are going to see, for example, here, let me erase this. For example, if you are going to have some curve that is denoted like this, whenever that you are going to choose this curve is fulfilling whatever that you are searching for, right? But the dashed line or the dashed curve indicates that there is a lighter shape lies above or to the right of the dashed curve. This means that above this curve there is some other curve which is solid. This curve is going to be exactly lighter. Lighter means that it's more economic. Okay, so do not say that this dashed curve is going to be enough for me. No, because it is heavy. If you are going to choose the first solid line, then it is going to be the lightest shape that is fulfilling and satisfying your needs. Okay, points on the curves corresponding to LP are indicated by a solid circle, as I have said before, and LR is represented by an open circle. So this is solid circle, which indicates exactly, this is here LP, and the open circle, it indicates LR. So here we have LR. Okay, so remember that they are indicating both. Okay, you are going to find this is solid, open circle. This is solid, this is open. So for each curve, for each shape, we have different values. This is LP limit, and this is LR, the proportional limit. Okay, I hope that you understand what we have mentioned up till now. Okay, now let's go to the next slide, which is related to the real curves. As you can see, I want you to stop the video and look to these curves. You're going to find it a little bit confusing, but anyway, this is how you are going to find it. Now you can understand everything on the curve, okay? Because you know the vertical axis, what does it mean? The vertical axis, what does it mean? And the solid lines and the dashed lines and the solid dots and the hollow dots or solid circles and hollow circles. As you can see, a lot of dashed lines here. For example, if we have a point here and I want to go up, then you are going to find this cross section. This means that this cross section is not going to be the lightest cross section for me. The next one is going to be the lightest, and so on. If I am, for example, if I am here, for example, or here, then if I go to the right, this is the dashed line, so this curve is not going to be the lightest for me. The next curve, which is this solid line, is going to be the lightest for me, and so on and so forth. Okay, so this is two different curves. As you can see, some curves it can show the horizontal lines, and other curves based on the horizontal unbrazed lengths. We started here from 6, 10, 14 and so on until we reach 30, 34, 38, 42 and so on. Then whenever that we go larger in terms of unbrazed length, you are going to see this part, which is always the hollow circle here. Means that the proportional limit is going to be there, as if that we are looking here, for example, and then you are seeing this part now, which is the hollow part, which is this part of the curves is going to be here. Okay. However, here, from here to here, for example, it is starting with the smaller unbrazed length. It is going to give you the plastic moment, for example, and the horizontal line is going to be shown here commonly. Okay, so this is how it looks, and now we are familiar with these curves. Okay, and one of the examples, only to show the point, of the dashed line and the solid line, and one of the examples that we have worked out before, 5.10, the required design strength was 810 foot kips, and there was continuous lateral support. Continuous lateral support means that LB equal to exactly 0. Okay. For continuous lateral support, LB can be taken as 0, as we said. If you go to the charts, from the charts, okay, the first solid curve above 810 foot kips mark is for wide flange 24 by 84. So this is the mark of 810, and then we're going to look up. Okay, then supposedly here we are expecting to have the smallest LB. We said that it is LB equal to 0, but actually in the charts you're not going to find LB equal to 0. Maybe you can start with 6, for example. Okay, so this means that you are searching for the mark with more than 810, and then you're going to check up. You're going to find the curve, the dashed line, with 29 by 83. So this is not going to be the lightest one. You need to go up until you reach this curve, the solid curve. The solid curve here is W24 by 84. It's lighter, of course, than the dashed line. The same as selected in example 5.10. If you revisit our video before, maybe I have worked this example. Maybe I'm not sure I've worked it or not, but anyway, I'm going to find it in the textbook. And this is only an illustration for what or how we can use the curves. Although LB is 0, is not in this particular chart, the smallest value of LB shown is less than LP for all shapes on this page. What does it mean? Let's go here. This is the curve here, and this is 810, and this is the limit, and this is where that we are. This is the solid line that we should take. If you are going to look, you are going to find that the first mark on the horizontal unbrazed length axis is 6. Okay, 6 feet. This is the smallest value on the unbrazed length axis. There is no 0. This means it's okay, because it means that we are having 6 foot as our minimum. If your minimum is 0, then this means that it's okay. I mean that you are in the safe side. Still you are in the safe side, and you are like within the limit. Okay, it's less than 6 feet, and this is what we are trying to say here. Although LB equal to 0 is not in this particular chart, the smallest value of LB shown is less than LP for all shapes on that page. Okay, so we are dealing with this one. Okay, next. The beam curves, the beam curve shown in the figure that we have mentioned before. This is something that is important for us, that for this one, for example, it was for compact shape. It was for compact shape. As we said, this is MP. It is for compact shape. Okay. So the value of MN for sufficiently small values of LB is MP. And this is what I have said here. For unbraced length less than LP, we are going to experience MP, which is the plastic moment. The plastic moment. Okay. However, if we have non-compact, then the non-compact curve is going to be something like this. Okay, going to be something like this, which is going to be on the curves. This is from form of the strength curve in the chart. They are going to show to you horizontal line, solid circle, hollow circle here. They are not going to indicate that it is compact or non-compact. They do not care about this point. You should know it from the beginning. So if the shape is compact, then this MP, the horizontal line, represents MP. But if the shape is non-compact, so this is the shape here, as it is, we are talking about compact. Okay. But here, this is the case where that we are dealing with non-compact. Okay, this is the case where that we are dealing with non-compact. The horizontal line, this horizontal line, is going to give us the flange local buckling strength for this shape. Okay, the horizontal line is going to be the flange local buckling, because in case of non-compact, we are dealing with, as we said, the failure mode in our case, whether that flange local buckling or inelastic lateral torsional buckling or lateral torsional buckling, right? So the horizontal line must be the flange local buckling, not web, because web it is always compact, right? So if it's non-compact, means the shape is non-compact, means that flange is the portion of the shape that is non-compact. This means that the horizontal line never ever would reach the plastic moment because it's non-compact section. Okay, so take care of this. In the curve or in the charts, you're not going to distinguish the horizontal line is MP for compact or flange local buckling. Okay, it is MP here or flange local buckling. You cannot tell unless that you check the cross section. It is compact or non-compact. Okay, this is only what I wanted to highlight, and this is actually what I have or the book is telling about us. But again, this is like what I have explained exactly. Okay, so take care that you are not going to find something called LP prime or dash or MP prime or dash here. No, you're not going to find something like this on the curves. This is what you are going to see on the charts, okay, in the charts. Something like this. That's it, okay. It is solid line, solid circle, and hollow circle. If this cross section is non-compact, then this line is going to be LP dash, which means that it is flange local buckling here. This is the strength of the flange local buckling. Okay, I hope that we could understand. Now let's go to the next part, which is related to the example, first example that we are going to have here. So we have this example. The beam shown in this figure must support two concentrated live load, as you can see, 20 K live load, 20 kips each at the quarter points, as you can see it. The maximum live load deflection must not exceed L over 240, it's given. lateral support is provided at ends of the beams. So we have lateral support at the end, means that the unsupported length LB for an unbraced length is going to be 24 feet. Lateral support is provided, as I said, use A 992 steel and select wide flange shape. This means that our F field equal to 50 KSI and wide flange. This means that we can use the charts. These are the two main conditions for us to use the charts. Okay, number one, we do not know what is the shape that we are going to use, right? So in this case, we can start, as we have explained in the design video, we can neglect the weight of the shape, okay? And then we are going to take it into consideration on a later stage, okay? So if the weight of the beam is neglected, the central half of the beam is subjected to a uniform moment, okay? If we're going to neglect the weight, we're going only to check the weight due to this live load. So it is going to be MA equal to MB equal to MC equal to the maximum moment. Okay, all of them, they are going to be the same. Okay, if we're going to have something like this, this means that all the moments at different points, at the quarter points and at the maximum and in the middle, it is going to be the same. Why we are searching for this point? In order to obtain CB. So now CB, if they are all the same, this means that CB equal to 1, as I have explained before. So this means that our CB equal to 1 and no need for us to adjust for the moment. Okay, so whatever the nominal strength that we are going to obtain from the curve, we are going to use it directly without any modifications. Okay. Even if the weight is included, it will be negligible compared to the concentrated loads, and CB can still be taken as 1, because maybe you are going to ask, if we take the weight of the beam, maybe the moments would be changed, but actually no, they are not going to be changed that much, okay, to be considered, and CB can still be taken as 1, permitting the charts to be used without modification. Okay, so this is number 1. Or this is, maybe we can say, the step number 1, as we have said and mentioned before. We need to be sure that we can use the charts. So first we have wide flange. Next we have F yield equal to 50 KSI. Third we have CB equal to 1. Then these are the prerequisite for using the charts. Okay. And then we are going to go and proceed for the next step, which is starting with LRFD. So we're going to start with the LRFD solution. If we say that temporarily ignoring the beam weight, the factored load is going to be 6 times 1.6 times 20. So we have 20, which is the concentrated load, 1.6. This is the combination factor. Okay. And we are having 6 feet, means that we are taking about the moment here. It is like 6, and this is 1.6 times 20. 1.6 times 20. So this is the moment here, which means that 20 times 1.6, 20 times 1.6, this is the factored like reaction here. Okay. And then 6, which means that it is the distance from this point to the other point, from this support to this point, which giving us the maximum moment here. So we're talking about 192 foot caps. Okay. Now after that, we are going to see what is the next step for our case. So we said that we have 192. Okay. Required. From the charts for LB equal to 24, we are going to try the first cross section for us. Let's go back. We mentioned here that the length is 24. Then we are going to the charts. Please stop the video and go to the charts now and check the wide shapes, available moment versus unbraced length, and go to the unbraced length, the horizontal line, and find 24 feet. Then go up until that you are going to reach the first solid line here. Okay, so we're going to have this. So from the charts with LB equal 24, try W12 by 53. Let's go back here. So the first solid line that you are going to find is this solid line, which is W12 by 53. When you go with this vertical line and get this point on this shape, wide flange 12 by 53, the horizontal line is going to give you these values for LRFD and ASD, 209 and 139. If we're going to make like zoom into this point or this part, you're going to find this is the point here, and here you're going to find where you are in. It is 210, 140, it is less than them. This is LRFD and this is ASD. Okay? Okay. Then we are going to try this cross section, and we found that this cross section is going to give us the phi BMN if we're talking about LRFD 209. However, that the required is 192. So it is okay in terms of the flexure strength. Now we are going to consider the thing that we have neglected in the beginning, which is the beam weight, right? So we are going to say M ultimate equals to 192, the moment coming from the live load that we have already explained before, and then we are going to calculate for the moment coming from the dead load, which is the weight. The weight is 0.053 because we are talking about 53, okay, pound per foot. So this means that 0.053 if we're talking about kilopounds times 1.2 because it is the factor, the load factor. Remember, 1.2 dead plus 1.6 live. Already 1.6 live, we already have done it before. So we are talking about 1.6. And then 1 over 8, it is simply like WL squared over 8. So here our L, it is 24. So it is 24 squared. W is going to be 1.2 times 0.053. It is the weight of the beam over 8. This is what we have done here. So remember 1.2, it is for the load combination. Okay. Then we're going to check. We found that it gives us 197 foot kips, which is less than the available strength that already we have got it from the curve, okay, which is 209. Then it's okay for us. Flexure, now this part, it is related to flexure. Let's erase. Okay, so now up till here, okay, this part here, it is flexure. Now we are sure that our flexure is okay, no problem with the flexure. Then we are going to check another thing which is related to shear. As we said in the design before, we're going to check for shear. For shear, we need to get the constant, the shear. If we're talking about this cross section, we need to get the value of the reaction at the support, which is the maximum shear. It is going to be 1.6 times 20. This is the concentrated load. Again, it is live load. The concentrated load, it is live load. Plus 1.2.053 times 24 over 2, which is going to be the distributed load coming from the weight. Okay, so of half of this. So we have 0.053. This is the load per unit length times 1.2 times 24 over 2. This gives us the reaction coming from the weight. Add it also here, and we are going to find that this is the ultimate reaction, required shear strength. As we have done before, going directly, we can go, and to accelerate the design process, we can go to the ZX table, or the uniform load table. Okay, we can go to the previous slide. This is ZX table, and we can go for W12 by 53. As you can see here, I'm zooming in on here. This is W12 by 53. Go to the last part. Last part is the shear strength for LRFD, and this is shear strength for ASD, which is 125 LRFD and 83.2 for ASD. Then go back. Then we're going to find that the value of VV times Vn equal to 125, which is much larger than 32.8. Then we are okay in terms of, exactly, in terms of shear. Shear is okay now, and flexure was okay. Now we are going into, or the last part, which is going to be related to deflection. Okay, we're going to get the deflection. The maximum permissible live load deflection, remember that we have only live load deflection to be considered. We are not considering dead load, as we said for steel beams. I have mentioned about this in the previous video, because the dead load always, or the weight coming from the own, or the own weight, is considered by using pre-campering. So anyway, they said to us there is a limit here, which is L over 240. Our L is 24 by 12, and over 240, this gives us 1.2 inches. Okay, from table 3-23, stop the video now and check this from the manual, okay, which is titled with shears, moments, and deflections in part 3 of the manual. Okay, we're going to find it. Next slide here, you can find this one. Okay, case number 9, simple beam. 2 equal concentrated loads symmetrically placed. You can find this on the table, but please do not rely on watching it in the video. As I said, stop the video and go and bring your manual and check how you can obtain it. You're going to find the deflection formula is going to be given to you here. And as you can see, it's the same, identical for our case. We have 2 concentrated loads, and they are separated, or they are dividing the beam into 3 equal, maybe equal parts, or I'm not sure equal parts or not, but at least the most left and most right parts are equal. So this is our case without a doubt. Then we need to know about P times A over 24 EI times 3 EI squared minus 4A squared. Everything is given here, and this is L, okay, not I. It is L, which is the length, okay. And we are going to find delta maximum. It is given for us here. It is at the center. So the maximum delta is going to be at the center. Okay, now let's go to the, sorry. So let's go back. We are going to apply this, and the maximum deflection at midspan, as we said, for 2 equal and symmetrically placed loads is as given in the table. No need for you to memorize this. It is given in the table. Know only how to bring it from the table. P, it is the magnitude of concentrated load. A, it is the distance from support to load, and L is the span length. Then you are going to substitute in this equation. You can go with this long equation, and you are going to find at the end the result is 1.1 inch, which is less than 1.2, our limit as given in the example. This means that we are okay. Our assumption from the beginning is going to be okay. We can use wide flange with 12 by 53. It is going to be the most economic because it is the lightest, and it fulfills 3 different criteria for us, which are the flexure, okay, it is related to the flexure, and shear, and deflection at the end. Okay, so we have the three main criteria that we need to check in this order, and we have used the charts. Okay, this is for LRFD. I think that we are having something missed for ASD. It is going to be pretty the same, so we do not want to spend a lot of time on ASD. It is going to be the same. Also, we are going to check for the flexure strength here. This is the part related to the flexure strength. And we are going to say that MA, the flexural or the required flexure strength, not including the beam weight in the beginning, 6 times 20. Okay, it's service load. Okay, 6, it is the distance, okay, from the reaction of the support, times 20, which we are something like that. There is here and here, so we are getting the moment here at this point. Okay, it is 120 from the charts with LB equal to 24. Try W12 by 53, same as LRFD. If you go back to the charts, okay, because we are, as we said, we are having the same. This is 24. Then the horizontal line is going to be given 139. We're talking about ASD here. Okay, so we are 139, as we said. It is much larger than 120. So this is already, we have done it before. Okay, and now 139 kips is larger than 120. So this is okay from the charts. From the same chart, actually, we have used for LRFD, but using ASD. Okay, the vertical axis would be for ASD. And then we're going to account for beam weight. So in this case, the beam weight is going to be 6 by 20 from the concentrated load and WL squared over 8 for the weight of the beam, which is the same, 0.053. This gives us 124, which is less than the design or the allowable strength for this shape. Based on that, the required shear strength, after that, this is the flexure. Okay, and after that we are going to talk about the shear. The required shear strength is going to be 20, which is the service concentrated load, plus half of the beam weight along the length, which is 24 over 2, as we said. This gives us 20.5 kips, and then we're going to get it from Z table or the uniform load table. Both of them are okay. We can obtain Vn over the safety factor. It equals to 83.2. From where? From Z table. Okay, Z table, as yes, here this is the ZX table, and you're going to find here 83 here. Zooming in, you're going to find it here 83. Okay, and then the last part is related to the deflection, but we are not going to calculate again the deflection. It is pretty the same as LRFD. So since deflection are computed with service loads, the deflection check is the same for both LRFD and ASD. Okay, and from the LRFD we found that 1.1 it was less than 1.2. Because deflection, as we said before, it is related to service loads. It doesn't account for factor load. So it works for LRFD and ASD both. Okay, similar also in ASD, flexure, shear, deflection, they are okay. Then our cross section, which we have chosen from the beginning, is okay. Okay, this is how it works for us. Okay, so now I think that it is okay for us. Remember well that our CB in this example was 1, so we didn't modify anything. Okay, although the charts are based on CB equal 1, they can easily be used for design of CB is not equal to 1. If we have CB that is larger than 1, then we can use this. We can use it. How we can use it? Simply, and instead, especially whenever that we're going to design, we can use the design strengths. For example, this is the allowable, for example here, 120. Okay, sorry, this is the required flexure strengths. Okay, it is going to be divided by CB, and then go the charts with this value, which is going to be 120 over CB. We're going to see this in the next example. Okay, before entering the charts. So simply divide the required strengths by CB before entering the charts. We illustrate this in the next example. Okay, so I'm going to illustrate this in the next example. I think that we need to finish as soon as possible to be within the limits, time limits for us. Okay, so this is, you can find this example also. We are going to go through it because it's very interesting example, and it is going to give us the meaning of having CB does not equal to 1. Okay, we have a 992 steel. We need to use it and select a rolled shape for the beam figure. So rolled shape means that we need to use wide flanges if we are going to use the figures, the charts. The concentrated load is service load here. This is service load. And the uniform load is 30% dead and 70% live, which is 3 kips per foot. Lateral bracing is provided at the ends and at midspan. So we have lateral support here. This means that our unbraced length LB equal to 12 feet. Okay, there is no restriction on deflection. It means that no need to check the deflection in this case. Okay. Now the solution, first of all, as we are making in the design, neglect the beam weight and check it later. We have distributed load, dead and distributed live load, 0.3 times 3 and 0.7.3 because we have the distributed 3. So we have dead load and live load distributed on the beam. So the ultimate distributed load, if we are going to start with LRFD, is going to be 1.2.9 dead plus 1.6 times 2.1 live. Gives us 4.44. And the P ultimate, it is only, they said that it's service load, means that it is live load. It is 1.6, okay, 9. 1.6 times 9, which means that the this is the P ultimate, 1.6 times 9. This is the ultimate, this is the load that being applied, the live load, and 1.6 the factor from the load combination factor. The factored loads and reactions are shown in figure 530. So this is the figure here, and this is the reaction that we can find here. Okay, it is symmetric. We are having symmetric. So our case is distributed load with concentrated load in the middle. This means that we need to calculate CB. Okay, we need to calculate CB. So for this reason, because we have like CB for the distributed load is like 1.3, for concentrated load it is 1.67, but we do not have the combination of the two. So we need to go to the first main equation for calculating CB, which is, as you can see here, 12.5 M maximum, which is the maximum moment, and 2.5 M maximum plus 3 MA plus 4 MB plus 3 MC. And you know where is MB, MA, MB, and C. Okay, it is going to be like quartering the span. Okay, quartering the span. Okay, so we need to know the moments at different places, at point A, at point B, at point C. Okay, so we are going to have point A, it is 3 meters from the beginning, 6 and 9. So here, this is 12, so we are going to have 3, 6, and 9. Okay, we need to know the moment here and here and here. We know the reaction, and we know the distributed load here, it is 4.4 K, so we can calculate the moment at each point here. This is at 3, this is at 6, this is at 9. Okay. Based on that, we can calculate these values from, we can use this equation, or you can calculate it easily by your hand. And this is easy, actually. This is based on the distance x from the lift support. But it is, I think it is easy for you to just at 3 meters here, you have the reaction times 3 minus the distributed load times the distance, which is 3, times 3 over 2. That's it. And then you can calculate the moment at each point that you want. Okay. Here only we put it in this equation to make it easy for you to get it. Anyway, we are going to calculate the moment at different locations. Okay. And then we're going to find these are the amounts of moments that we have, the magnitudes, then substitute in CB equation. After substitution, we found that CB equal to 1.36. So it does not equal to 1, okay? This means that our charts need to be modified. So instead of changing, we can change, of course, the charts. We can change the charts. Anything coming from the charts, we can multiply by 1.36. Okay, this is okay. Another way is to get whatever the ultimate load that we have obtained, or the ultimate strength or required strength, divided by 1.36 and enter the curve. Okay, both are okay. Okay, enter the charts with unbraced length LB equal 12. As we said, we are having unbraced length, okay, to be 12. 12 foot and a bending moment of M ultimate over CB. M ultimate over CB. That's what I was telling, that you can get it from this part. Get it from this part. M ultimate over CB. So it is going to be 406.1 over 1.36. It is giving to you 299. 299. Okay. And after that, try wide flange 21 by 48. 21 by 48. I think that I put it here. Okay. So now you have this value, which is the required moment after being modified by the CB. Okay, this is okay, no problem with this. It is similar to going with 406 and multiplying and multiplying whatever that you are going to get from the curve by the CB. Okay. So now let's try this. Why we try this? Let's go. We're going to horizontal axis. This is 12. And then we're going up until that we can find something that is giving us the value that is 299 or above. Okay, so we are going here. This is 250, so we are here. We're going with this line until we reach, this is 300, so we are like getting 299 here, and this is going to be like this, so we are here. Okay, I hope that, yes, I have it like this is where we are. Okay, this is 12. Okay. Okay, and this is like the point that we can get, it's 311. 311. Here, this point, it is on this shape, which is W 21 by 48. 21 by 48. Okay, for the unbraced lens of 12. Okay, now let's go back. Based on this, you are going to find phi b times mn. It is 311 foot kips. This is for CB equal to 1. No problem now for us. Okay, no problem now for us. Since CB equal to 1.36, the actual design strength is, this is the actual design strength supposedly to be CB times phi b times mn, right? This is what supposedly to be the case. So we are going to multiply 311 by 1.36 CB. It gives us 423 foot kips. But if you look to the curve, that is related to wide flange 21 by 48, we're going to find that this curve ends at moment mark equal to 398. So our potential, or based on the CB, our design strength is going to reach 423, which is higher than the plastic moment because this shape is compact. For example, if it's compact, then this horizontal line is going to be the plastic moment. We cannot exceed the plastic moment, but the design strength cannot exceed phi b times mp because it is the plastic moment, which is only 398. This is the limit here. Obtained from the chart. This is obtained from the chart. Okay. So if we go back, so here, okay, this is the line here, but we cannot see where it ends. Okay, I think that I have something here. Yes, here it ends. So I put it like this. So this is W, next solid line upward. So yes, this is W 21 by 48. As you can see, this is the solid line here, it seems here, and this is the horizontal line. This is the plastic limit. We cannot use this one. Okay, we cannot use this one because our capacity is going to exceed even 398. So this means that we need to go to the next line, the next solid line. So this was the previous solid line. Now going up, we found dashed line. So this means there is lighter shape above. We go above, we found this shape, which is W18 by 55. This is what we call it, the next solid line upwards. Okay, the next solid line upwards. This is whenever that we are going to hit this solid line, we are going to find that it gives us horizontal value of 335. 335. Okay, so in this case we said that this is the maximum for us, and then 300. The actual design strength must be taken as, okay, phi b times mn, which is 395. Okay, and this is less than 406, as we said, which is not good. Then we are going to try the next shape. So we're going to move up, as I have shown you a few seconds ago, and the charts to next solid curve. So we are going up to the next solid curve and try, this curve was W18 by 55. For LB12, this is for the same LB12. The design strength from the chart is 335. When we hit this curve, it was something like this, for example. Okay, and we found that when we hit it, we found that it is 335. 335. Okay, so this means that for CB equal to 1, take care, we're talking about CB now equal to 1. The strength for CB equal to 1.3 is 1.36 times 335, which already we have obtained. It must be less than this value. How much this value? Okay, this value is 420, which is what? It's the plastic limit for this shape, for wide flange 18 by 55. From where we got it? You can obtain it from the curve here. This is wide flange 18 by 55. If you go up, and you are going to find the horizontal line ends with 420. Okay, so this means that 420, okay, is larger than 406. This is the M ultimate. This is the required strength that we were talking about. Before it was larger than 398, but now it is less than 420. So this means that this shape is okay for us now. For flexure, it is going to be okay. Okay, but still we need to check something else, which is the beam weight. We need to check the beam weight. So M ultimate, considering the beam weight, is going to be the M ultimate here, 406.1 plus the additional weight. As I said, the additional weight WL squared over 8 and multiply by 1.2 factored load, 0.055. This is the dead load unit weight of the shape, which is 55 here. Okay. This gives us 411, still less than 420. Then flexure wise it is okay. Until here we ended the flexural part. Okay, then the remaining part is going to be the shear part, the shear or the shear strength. Okay, so the maximum shear strength is going to be 60.48. This is coming from the reaction from the loads that we have explained, the loads already on the beam. Okay, this is the loads already on the beam, 60.48. And then, oh sorry, this is 60.48. This is 60.48 and plus 1.2, 0.055 over 2 times 24, which is the total length of this beam. 1.2, again, it is the load combination factor for dead load. 0.055, it is the self-weight per unit length of this shape, which is 55 pounds per foot length, and over 2, which means that we are having the distributed load reaction for half of the length, because we are talking about the reaction, for example, on the lift. So it is going to give us 61.3 kips. 61.3 kips. From ZX tables, as we have mentioned before, please stop the video here, go to the ZX table and check for this shape, which is W12, W18 by 55. Check what is VN value, the shear strength value. You're going to find it 212 kips, and it is much larger than the required ultimate shear strength, which is 61.3 kips. Okay, so this means that we are okay now. No need for us to check anything related to the deflection, because already it's being given in the example that no need to check for deflection. Okay, so it is important to highlight the last thing in this video, which is related to the CB. In this example, which is 5.12, the value of CB is the same to 3 significant figures for both the factored and unfactored moments. The two computed values will always be nearly the same, and for this reason it makes no practical difference which moments are used. And this is true, and maybe it is like we can say it is something we can find logic. The two computed values will always be nearly the same. If deflection requirements control the design of a beam, so if we are going to have, as we said, we have flexure, shear, and deflection. If deflection is going to control the design of a beam, a minimum required moment of inertia is computed. So take care of this approach. We need to compute minimum moment of inertia is computed. And the lightest shape having this value is sought. This task is greatly simplified by the moment of inertia selection tables in part 3 of the manual. And this is, you can find it in the textbook for example 5.13 in the textbook. I'm not going to explain it, but you can find it in the textbook, and the information there is pretty similar to what we have explained before, but it is good practice for you to know if in this rare case where that deflection is going to control how to design the beam. Okay, but as I said many times, this is not the common case. Commonly, flexure is the determinant factor for the design of beams. After that, we can check shear and deflection, and rarely we can find shear or deflection to control our beam design. Okay, this is, I think that by this we reach the end of this video. I hope that you understand, you have understood what I have explained today. Remember well that the charts that we are dealing with in today's video, it is related to wide flange only. And remember the hints that I have mentioned about the solid circle and hollow circle, what is the difference between them. And remember that we are talking about compact, and if we are dealing with non-compact section, this means that the horizontal line on the curves or on the charts is going to give us flange local buckling. And if we are going to design and we found some dashed line, we can always go up or to the right in order to get the lightest shape. Remember that CB for all curves is always 1. In other cases where CB does not equal to 1, this means that we need to go and multiply the curve by the value of CB, whether it is, for example, 1.6 or 1.7 or whatever. Then we need to multiply whatever that we obtain from the curve by 1.6. But remember well that this value need not to exceed the plastic limit here, which is M plastic in our case, okay? Or the flange local buckling, for example, if we are talking about non-compact section. So this is like summarizes what we have done for today. I think that the basic principle is very easy to be understood, but you need to work out more examples. Try to solve the 2 examples that I have explained today by your own, and try to go through the manual charts by yourself. And through that, you can through this you can find yourself familiar with using the charts for beam design. Thank you, and see you next video.